Hey everyone, welcome back to The Explainer. I'm so pumped you're here today because we have a very specific, highly actionable mission ahead of us. We are going to completely conquer the exact FDM 3D printing procedures you need to know to pass your upcoming lab evaluation. Now, if you've been staring at your lab notes feeling, totally overwhelmed by all the parameters, the materials, and those tricky machine zeroing steps, you are absolutely in the right place. We're going to break the whole thing down visually, step by step. That way, when you actually step up to the machine, you're going to look like an absolute pro. Let's dive in.
Here is our roadmap for this evaluation prep. We'll start with FDM 3D printing basics, move into a filament guide covering ABS, PLA, and TPU, hit the machine specs and supports, and finally wrap up with mastering offsetting.
All right, kicking things off with Section 1, FDM 3D Printing Basics.
So, to pass the written portion of your lab, and frankly just to understand what you're doing on the bench, we really have to define what this machine is doing when you hit Start. FDM stands for Fused Deposition Modeling. At its absolute core, the machine melts filaments, prints them out, and then the material hardens right up when it cools down. Now, I want you to focus on two massive keywords here, additive and layer by layer. See, this isn't a lathe or a mill where we're cutting material away. This is an additive process mostly used for rapid prototyping where we build up the model one single cross-section at a time. Getting that precise mechanism straight in your head is totally essential for your foundational understanding.
And this brilliantly illustrates why we even bother learning this in the first place. Just look at the incredible range of real-world applications for 3D printed polymers. We are literally talking about prosthetics and replacement implants, aeronautics, space travel, civil structures, automotive parts, and electronic components. Keeping this big picture in mind really grounds the theory before we start getting into the weeds with those tricky, highly specific machine parameters you'll be tested on.
Moving right along to Section 2, our filament guide covering ABS, PLA, and TPU.
Listen, I have to warn you right now, choosing the wrong environment or temperature for a specific filament is a guaranteed way to just instantly fail your physical test. You cannot treat these plastics interchangeably. There is a stark, direct contrast between our two main plastics here, ABS and PLA. Just look at the printing temperatures. ABS demands high heat. You're looking at a minimum of 230 degrees Celsius up to a maximum of 250. PLA, way lower, at just 195 degrees. Also, ABS needs a heated bed between 80 and 100 degrees, while PLA doesn't even need one. But honestly, the real test maker here is the environment. ABS requires a strictly closed printing environment with absolutely no cooling fan. PLA, on the other hand, needs an open printing environment, and it absolutely depends on that cooling fan. You've got to memorize these distinct pairings because getting them crossed is a critical error.
Actually, I want to stress this next point with absolute strictest because it trips up so many people in the lab. When you are printing with ABS, you must use a closed environment with zero cooling fan. None. The lab notes make the consequence of this super clear. If the fan hits your ABS print, the plastic cools way too fast. That causes it to shrink, which ultimately causes your model to just crack right there on the bed. So, no fan for ABS. Period.
Now, on the complete flip side, PLA is highly sensitive to heat retention. It's basically the exact opposite of ABS. If your PLA isn't actively cooled down while it's printing, the material stays way too soft and the whole model will actually tilt and warp on you. And that is exactly why open printing and active cooling are strictly required when you select PLA for your lab practical. Just real quick, to round out your material knowledge, you also need to be familiar with TPU, which stands for thermoplastic polyurethane. Whenever you see TPU on an exam, I want you to instantly associate it with one word, flexible. It's the flexible filament alternative. And just as a heads up, across the board for these lab practicals, the standard filament diameter you'll be working with is 1.75 millimeters. Okay, Section 3, machine specs and supports.
Knowing the physical limits of the hardware is what prevents dangerous and honestly pretty costly errors during your evaluation. I'm going to rapid fire these crucial hardware limits for you. Treat these as definite test questions you need to lock into your memory, okay? Your maximum model size on the X and Y axes is 220 millimeters, and on the Z axis, it's 250 millimeters. The absolute maximum temperature that nozzle can handle is 260 degrees Celsius, and the bed maxes out at 110 degrees. Furthermore, remember that the infill setting is what actually provides the structural strength to your final product. Oh, and when the machine performs bed leveling, it relies on a proximity sensor, and the stepper motor driving the filament uses a 2-gear system. Lock those stats in.
Now, alongside the machine hardware, you have to tell the software how to physically support your print. Obviously, changing the angle or orientation of your model increases or decreases the supports, material, and time you need. But you specifically need to know when to use the two main bed adhesion types. You're going to use a brim specifically for flat models to help them stick to the bed. But you'll use a raft specifically when the height of your model roughly equals the diameter of its base. That essentially gives a tall, narrow part a much wider, more stable footprint so it doesn't tip over.
Which brings us to the big one. Section 4, Mastering Offsetting. We have officially arrived at the climax of this explainer. This is where the rubber meets the road. Before you can print a single layer, you have to ask the machine this exact question. Where is absolute zero? You really have to shift your mindset from the digital file on your computer right down to the physical, real-world space of that glass printing bed. Because the crucial point is this: the machine is completely blind until you orient it. Machine 0, which is also known as the home position, is the exact coordinate 0, 0, 0. It is the absolute zero starting point for the machine offset. You literally cannot begin the actual 3D printing process until you've established this physical baseline.
So here is the exact, systematic sequence straight from your lab notes. First, ensure your Z offset is cleared out and set to 0.00. Second, navigate through the printer menu, go to Move Axis and select Home. Third, and this is super critical, you deliberately move the tool head to the exact center of the bed by moving X to 110 millimeters and Y to 110 millimeters, while keeping Z at 0.00. Why 110? Well, remember our maximum X and Y sizes from earlier were 220, right? So 110 puts you dead center. Fourth, you perform the paper scratch test. Once you're fully calibrated, step 5 is to finally, confidently hit print.
All right, let's talk about how this actually translates to the physical test itself, the famous scratch test. You're going to use the thickness of a standard piece of paper slid between the nozzle and the bed. But listen to me, here is the vital safety step. You must first raise the Z-axis to positive 1.00. If you skip this, you risk driving a superheated nozzle straight into the glass bed and totally ruining the machine. Raise it to +1, slide your paper under there, and then slowly lower the Z offset until you feel a light scratching drag on the paper. According to the lab notes, this will usually settle around negative 2.50.
There is a golden rule right in your lab notes for FDM printing. Offsetting dictates where absolute zero is. If wrong, won't stick. It really is that simple. If you rush through the scratch test and your nozzle's too far away, you aren't printing a model, you're just printing a messy ball of plastic spaghetti into the air. The literal consequence of a failed calibration is a failed print, which means a failed lab.
Okay, take a deep breath. Look at how much we've covered today. You now know the vital differences between ABS and PLA. You know the exact hardware limits of the FDM machine. And, most importantly, you know the precise, step-by-step menu commands and safety protocols to find absolute zero using the scratch test. You have the structural knowledge to not just operate the equipment, but to actually understand exactly why it operates that way. So, my final question to you is, are you ready to step up to the printer and ace this practical? I definitely think you are, but once you conquer absolute zero on this machine, what kind of impossible geometries are you going to build next? Thanks for joining me on this explainer, study hard, and I'll catch you in the next one.